Welcome back to the Deep Dive. If you've ever wondered what a real theory of everything might actually look like, well, I think this is the deep dive for you. For, gosh, over a century now, physics has been sort of broken. You have the cosmic scale, general relativity, where we're stuck with these huge mysteries like dark matter and dark energy. And then you have the quantum scale, the standard model, where we're just forced to accept these really bizarre paradoxes like wave-particle duality. The sources we're looking at today focus on this radical new proposal that's designed to heal that split. It's called Expanse Tension Theory, or ETT, and its bigger version, GETT. So our mission today is pretty ambitious. We're going to unpack how a single unified field theory claims to just sweep away all of it, the cosmic anomalies, the quantum paradoxes, all with one surprisingly intuitive, deterministic idea.
And to really get it, we have to jump straight into that core mechanism. The whole thing, every prediction, it all hinges on one entity, a scalar field. The researcher, John Holland, calls it the Holland field. The best way to think of it isn't as a particle, but more like a property of space everywhere, like a temperature map or a pressure map.
Okay.
And the really critical part is that this field is proposed to merge with the Standard Model's Higgs field. So you get this Holland-Higgs field theory. And the one idea driving everything is density dependence.
Density dependence.
Yeah. The idea is that the fundamental rules, the constants themselves, they shift just a little bit depending on the local mass energy density, which we'll just call.
Okay, let's unpack that. Because if this is a theory of everything, it has to work at the biggest scales first. So let's start with the cosmos. How does this single density-dependent field get rid of the need for dark matter and dark energy?
Right, so this falls under what the theory calls ETT Hypothesis 3. The idea is that gravity, what we feel as attraction, and the expansion of the cosmos are, they're actually tightly linked. They both emerge from this modulation of mass expansion coupling.
And that modulation is controlled just by the local density?
Just by the local density. So in a high-density area, like, say, our solar system, the field behaves one way and you get plain old Newtonian gravity. Everything works as expected.
But if you move out into the much lower density of a galaxy's halo, the field changes, and that mimics dark matter.
Exactly. The math itself defines these critical density thresholds. When the local density drops below a certain point, around 10 to the minus 21 kilograms per cubic meter, so incredibly sparse, the field shifts into what's called the Holland mode.
A phase change.
It's a phase change. And that change strengthens the apparent gravitational pull without needing any extra mass. It just naturally predicts the galaxy rotation curves we see.
Wait, I have to stop you there. This sounds conceptually a bit like MOND, modified Newtonian dynamics. That also proposes changing gravity at low accelerations. How is this different?
That's an essential question, really. And they seem similar on the surface, but MOND is what we'd call a kinematic modification. It just proposes a change to Newton's law of acceleration. It's an adjustment to a rule.
Okay.
ETT is fundamentally different. It's a field theory that grows out of quantum field theory. It doesn't introduce a new law. Instead, it changes how mass itself couples to the expansion of space, all based on the local field conditions.
So the MOND-like results are just an emergent property.
Precisely. It's an emergent property of the field's dynamics, and it still remains perfectly consistent with the standard model in places where the density is high.
That distinction is absolutely crucial. Okay, so what about dark energy? The thing accelerating the whole universe.
You just keep dropping the density. If you go out into the great voids between galaxies down to, say, 10 to the minus 27 kilograms per cubic meter, the coupling between mass and expansion basically just collapses.
Another phase shift.
Another phase shift. And that's what causes late-time cosmic acceleration. It's the field itself changing its state. So you get one explanation for both dark matter and dark energy effects from the same field using the exact same mechanism.
Wow. That's an enormous conceptual win. The biggest cosmic mysteries just solved by saying physics depends on density. Okay, let's flip the script. Let's go to the complete opposite extreme, ETT Hypothesis 3, Part B. If low density messes with gravity, what happens when the density is insane, like inside a black hole or a neutron star?
Right. We're going from the cosmic void to the most compressed matter imaginable. And here, ETT Part B looks at something called Higgs symmetry restoration. So, just as a refresher for everyone, the Higgs field is what gives fundamental particles their mass. In normal space, the Higgs field has this background energy level. It's what licenses mass, and by extension, things like inertia and even time itself.
It licenses them. I like that word for it. So what's the prediction at ultra-high density? What happens to the license?
The license gets revoked. The theory says that when matter is that dense, the pressure becomes so immense that the Higgs field's background value collapses to zero.
And when it happens?
All the things it supports, gravity, inertia, proper time, they de-emerge. They just cease to exist in their normal licensed form.
So a black hole isn't a point of infinite gravity. It's a phase boundary, where mass and time literally break down because the fields can't support them anymore.
That's it, exactly. And this is where the theory gets really elegant. The analysis derives something called a restoration radius, RCRIT, purely from quantum field theory. It calculates where this phase transition has to happen.
But hold on, how does mass, the m in the equation, even get into a QFT calculation if you're not starting with general relativity? That seems like the key connection.
It is. It enters because the calculation depends on the total mass energy inside the volume that's driving up the density. So by analyzing the field's behavior around that energy distribution, the theory derives a radius that, well, it naturally matches the classic Schwarzschild radius.
It derives 2gm over c squared.
It derives the Schwarzschild radius without ever assuming general relativity. The constants g and c just emerge from the calculation as boundary conditions for the licensed effects they described.
So the event horizon isn't a geometric thing, a curvature of spacetime. It's a quantum phase boundary where the license for mass and inertia just fails.
That is the core insight. It turns these incredibly mysterious objects into, well, field-theoretic phase transitions, and that even links up to things we observe, like the certain glitches in the rotation of neutron stars, which we think are caused by phase changes in their core.
That is truly mind-bending. The scope here is just incredible. Okay, let's make the sharpest turn possible. Let's come all the way back to the lab, to the most stubborn problem in all of quantum mechanics, Young's double-slit experiment. This one experiment has basically forced us into accepting wave-particle duality for almost 100 years now. How does GETT claim to have a deterministic solution for it?
This is where the general part of GETT gives us this beautiful mechanistic picture. In GETT, all matter, an electron, a photon, whatever, is modeled as a localized core excitation of that scalar field. It's a real physical particle. But, and this is the key, that core excitation also creates these tiny little perturbations in the field all around it. The theory calls them expanse tension ripples, or ETRs.
So the particle is the core, and the ETR is like its physical pressure wave in the field.
A pressure wave is a great way to think about it. And these ETRs, they propagate out at near light speed along with the particle. Now think about the two slits.
Right.
When you fire an electron at the barrier, the tiny particle core, it goes through one slit or the other, deterministically. But it's ETR, this vast, diffused pressure wave.
It goes through both slits at the same time.
It goes through both slits. And just like ripples in a pond, they interfere with each other on the other side.
And that creates an interference pattern in the field itself.
Exactly. It creates a dynamic tension landscape. The electron, which has just passed through its single slit, is now flying into that landscape, and it gets continuously guided by the local tension gradient.
I see it now. So the particle itself isn't a wave. It's a particle being steered by its own physical wave. It's guided toward the bright fringes, the areas of constructive interference. But this sounds a little like an old hidden variable theory, the kind that Bohr argued against. What makes this different?
The key difference is that these ETRs aren't hidden, not at all. They are calculable physical excitations of the fundamental field. Classic hidden variable theories proposed unknowable things. Here, the entire process is deterministic, it's predictable, and it rests on a single permitted QFT concept.
A physical wave guides a physical particle.
And that's how you get the statistical fringe pattern over many shots. Wave-particle duality just it ends. We don't need it. We don't need wave function collapse. We just have a clear physical process.
That is the core takeaway here for you listening. The century-old mystery just dissolves. So we've gone from the cosmic web to a black hole to a single electron in a lab, and we've solved the biggest mysteries at each scale with the same mechanism. Let's zoom out one last time. GETT, Hypothesis 4, the theory of everything.
This is where it all ties together. Hypothesis 4 introduces the universal coupling modulation equation, or UCME. And the claim is, well, it's that the single Holland-Higgs field doesn't just manage gravity and mass. It dynamically modulates every single parameter in the Standard Model.
So you're saying our fundamental constants aren't actually constant?
They're not, at least not universally. All particle masses, the strengths of all the fundamental forces, mixing parameters, even the gravitational constant g, they're all seen as emergent, density-modulated parameters. If the density of space changes, the local physics subtly changes with it.
This has to have huge implications for some of the big tensions in cosmology right now, right? You mentioned the Hubble tension.
It does. The Hubble tension is this nagging disagreement between how fast the early universe was expanding and the rate we measure locally today. But if G, or the strength of electromagnetism, is just slightly different in high-density regions versus low-density voids, which is a direct prediction of GETT, that could resolve the entire tension.
Without needing any new physics.
Exactly. And it's the same for those little hints we've seen that the fine structure constant might not be the same everywhere we look in the cosmos. GDT provides a physical reason for why that might be happening. It's the density.
And the sources really stress the elegance of this. It's, what, the first known, renormalizable, minimally extended standard model that fits all the data, explains the anomalies, and does it without needing extra dimensions or a whole zoo of new particles.
When you really synthesize it all, that's what stands out, the elegance. It makes the universe a place defined by phase transitions, like water to ice, rather than a list of arbitrary fixed numbers. And the link is always density dependence.
We started this deep dive with a theory that redefines, well, everything, from what a black hole is to how light behaves in a lab. I think the biggest significance for you, the listener, is the claim that we can use established QFT concepts to get a deterministic, intuitive answer to paradoxes we've lived with for a century.
And that leads to a really profound final thought to leave you with. If gravity, inertia, and mass are all licensed by a field that can collapse, and if the constants we build our science on are just density-modulated parameters, where else in the universe are we missing these density-driven shifts? The physics in our lab might not be the physics everywhere.
Absolutely fascinating. That's a deep dive complete. We'll see you next time.